Johan Paulsson, I'll just let you take over for running 5 minutes like you.
Yeah, it's great to be here. It's nice to have such a high-quality conference 2 blocks from my house. Thanks to the organizer being understanding with the scheduling. My family's visiting from Sweden for a few days. I apologize for not being on the top schedule. Right, so I guess my background, I'm more from applied math. My group started in applied mathematics and critical physics in the other Cambridge. And then 15 years ago, we moved over because we wanted to work more on experiments as well. So I guess most experimentalists I know, they have 1 or 2 systems that they focus on. And in applied math, you have more of this, everybody wants to be sort of Sauron with a big, all-seeing, all-controlling eye, power. And I guess I had that syndrome as well a bit. So developing that case in many different problems before becoming a experimentalist meant that we now focus on tons of different things. So we work, almost every student and postdoc works in a completely different project. I'd say that the last 5 major papers have been on 5 entirely different topics, from the structure of the ribosome to segregation of organelles to synthetic oscillators and so on. So we work, it's not like we're having like a fading interest in some of these topics, it's more that we've worked on them for 5 to 10 years, and we're actually trying to push hard on all these things. And then the last few years, we also moved over more towards engineering and applied work. That's partly because many of the mathematicians that join my lab, within a few months, they get sort of data and they want to become experimentalists. So several of the people that I hired to do theory, they become pure experimentalists. They never pick up a pen essentially. And they also gravitate towards more technology solutions. So that means that we spend a lot of time on sort of infrastructure and methods and so forth. So now we have this issue where we're essentially getting a bunch of results on the engineering side. My interest is much more somewhere between these two, I guess. But we're developing methods for solving these problems and mathematical tests and so forth, tests of the mathematics, put us in a position where we can engineer things, and this gives much more money. And now I'm facing this issue that by getting money from these people, then these people say, I don't need any more money, so I can't do any more math. So it's kind of a bit frustrating, but shouldn't play too much, I guess. So, all right. In terms of the type of math we do, I guess there was a comment by Peter yesterday that instead of starting with a simple model, and then when you get more data, you add whistles and bells to it. Peter mentioned that another approach here is you start with something large so that you don't forget stuff that you otherwise would have forgotten. But then once you have that, you try to converge it with something that's simpler and see if there are any broader principles. And that's pretty much the sort of guiding principle for everything we do. We try to start broad and narrow, and try to get something that's as broad as possible. And in terms of theorems and laws, I think that maybe there aren't any laws in biology saying that these class of systems will always do these kinds of things, because there's so many exotic things that are going on. We're not near equilibrium, we can't really make use of the physical law in the same sense. I think one thing to remember here is that many of the most influential physical laws are negative, in the sense that they describe what cannot happen. The first and second law are things that cannot happen in thermodynamics. And I think that's something that there's at least an intellectual possibility that there are such laws in biology. Because you could say that there are certain classes of systems where a few things are specified, but other things are left completely open. And you can't say what they do, obviously, because you don't specify everything, but maybe you can say what they cannot do. Right? Just to see what I mean by this is maybe the only example of a Swedish theorem I know. You have 2 coupled differential equations. Let's say it's a chemical system where they both control each other's production rate with some arbitrary functions, and they both decay exponentially. Then depending on these parameters of the functions, you can get something that's bi-stable. If you start too low, you go down here, start higher, go up here. You can get things that are damped oscillators. What you cannot get, according to the Dixon-Slater criterion, is a stable limit cycle. There are no functions that tolerate that. So this is related to the fact that, or similar to the fact that you need 3 variables to get low-dimensional chaos. So what we try to do here are 2 things. One is that we don't look at ordinary differential equations, we look at marker processes instead. And then we try to see if we can handle one big restriction on all these conclusions, which is topology. Here we say there are only 2 variables, and that's one of the big assumptions here. In a real system, how do you know that the 3rd variable is really can be ignored, or the other 3 million variables in the system can be ignored? Right. So the first issue here is the stochastic. So here's an example of a chemical reaction network. We go here from a discrete number of molecules, so from 9 to 10, and from 13 to 14, and 27 to 26 or something. And the rates here are now transition probabilities, or propensities, so they're probabilities per second that the reaction occurs. So this forms a two-dimensional master equation that you can simulate with Gillespie, or which was developed by Dube in the 40s, the exact simulation algorithms. And we can get these time traces. And it's not that hard to find functions and parameters that give you a kind of an oscillation that persists forever. And in fact, the difference between a stable limit cycle that is corrupted by noise versus a damped oscillation that is rescued by noise, it's not clear to me exactly what the difference is. So it's more, instead of saying oscillations are impossible or possible, it becomes more a question of quality. Like, to what extent do you have coherence? What's the phase drift and so forth? So maybe you can predict quantitative numbers based on topology. Maybe there's no two-variable system with any rate functions that have unlimited phase drift. One thing we noticed, though, is that if you take the system and we vary the parameters, vary the functions, we run these simulations for billions of reactions, we collect the statistics, and then we calculate things like the average here, so the angular brackets or the variances, and we calculate the variance over average for one, the variance over average for the other, and we plot it. So one sort of long-term simulation will be maybe this done up here. Then we change the function, change the parameters, maybe end up here, here. We cannot find functions or parameters that get you into this closed box. Yep.
Just curious, so what's the class of functions f and g that you typically look at here when you're doing these?
When we do it numerically, we first start out just looking at ratios of polynomials,
rational functions,
yes,
so classical
exponentials,
functions.
But then we also start saying, okay, if we reduce the state space, we have low numbers of molecules, say we only allow from 0 to 10 molecules, then we can go in and change, because then we only have to worry about the rates at those 10 positions, so there's only 20 rates, so your function only has 20 values. And then we can start taking like random values, where we're just trying to make things that are like completely, like crazily non-monotonic and so forth.
Oh, so you're not going to assume that f and g are monotonic in this case?
Yeah.
It could be originality.
Yeah. And what can do, so this is again, a two-variable result. This is work by Andy and Jagwe and the like. If you have more variables, there turns out there appears to be other impossibilities. Even if you have a fully connected network, as long as you can't affect your own production rate, then all the effects on yourself are indirect via another component, there are still these sort of hypercubes that you can't enter. So essentially, it seems that there are some, if you want to suppress fluctuations of one component, other components cannot be suppressed. So you have to have these sort of sacrificial components. You can think of them maybe as signals in the cell that they don't do anything except control the things that do stuff. So this whole paper we worked on for many years, could never prove it. In the end, we just gave up and we published the conjecture.
Even with assumptions like rational functions for the f and g?
Yeah, we cannot prove it. If it's nonlinear, we can't prove it. So we can prove it in two limits. In the high boundless limits, it proves easily. Write down linear noise and the optimus over all parameters, falls out immediately. You can also do things in the low boundless limits with like sort of market decision processes and Bellman approach and so forth, where you can do exhaustive searches. So in the high boundless limits, low boundless limits, you can prove it. In the medium regime, you can take all these rational functions and ratios and so forth. And every single simulation algorithm we devise gets as close to this line as we like, but nothing breaks it. And then again, if you have handfuls of molecules, you can do this very systematic, like millions of combinations of where every rate function essentially is. And again, we can get to any point, you can't break it. So I say I'm very confident that it's true, but it is a conjecture, it's not a mathematical proof. It's a computational biology, it's a proof.
What if the reactions are not instantaneous? What if reactions are not instantaneous?
Yeah, so then you can break it. So having non-instantaneous reactions, essentially if you say that this can depend on the history of variables, that's essentially similar to introducing another variable in the system with instantaneous, and then you get different limits. So you still get some limits, because even in the fully multivariable case, you get some limits, but it's not the same limits.
Is the nature of this forbidden region clear from the structure of the graph?
Not really sure what that means.
Well, you have different forbidden regions for different
Yeah.
graphs. Is that relationship understood?
No, I mean it's the only thing we've done essentially is we tried a few graphs, and then we tried to devise a proof for that graph. So this is almost everything we did. We did a few other things. We said, okay, what if we actually you can affect yourself, but not in with any function that you like, but something that's limited, like maybe Michaelis-Menten negation or something, or negative feedback, but with a limited Hill coefficient or something like that. So we can expand it to that. But otherwise, this is more or less it. And I think that's a great question going forward. So my suspicion here is that this is sort of the tip of the iceberg of a rule that with some method that we can't figure out, and we've tried, every single person who joined my lab in the last 10 years have immediately said they can solve this. And then after 2 months, they give up. And we tried so many different approaches.
So why Fano and not CV? That's the only thing I don't understand. Why Fano and not CV?
We're not assuming this could be one or the other. This is the thing that's constrained.
Okay, but if you do
want the
CV,
intuition?
then there's no constraints?
Then there's no constraint. No,
Wow,
because then
I see.
see there's no constraint. So this is also a sort of two one-variable processes controlling each other. So I think that's the intuition of what should be the thing of the CV.
And is this, all of these, you're always thinking about some kind of exponential decay, some kind of self-decay is in there. Is that important?
It's important in the sense that if we change this assumption, we get different boxes. So if we for example, allow x1 to the power 2 here, then I think this cube collapses to like a quarter of a sphere. Something like that. So you still get bounds, but it's not important in that sense, but certainly you don't get the same result.
But there is always decay.
Yeah, otherwise it won't be stationary. These are also stationary. Right. So maybe just two more questions on this, because this was just an introduction.
I was just wondering whether you can say something generic about the solutions at the boundary, whether there's something in common.
Yeah, no, that's actually an interesting question. It turns out that, so one way of getting to this point is trivially not having control. Like if f and g are constant, both are Poisson, you get to this point. It turns out that once you run these simulations, you also find examples of things that are extremely intricately controlled, where they're massively affecting each other, and they also end up exactly at this point. So the boundary seems to be achievable in many, many different ways.
How about the effects of cell division? Like, at least in station state, but if you consider cell division,
So almost in all our papers, we do consider cell division. So this is actually something that we've made experimental focus and mathematical focus of the lab for many years to say, what happens if instead of these being degraded, or maybe in addition to these being degraded, you have a growing and dividing cell, you have some partitioning at cell division, and then you can do that. So many, many of our papers focus on analytical solutions for cell division. Even the papers where we say this is really important, we end saying we don't recommend other people do this, and the reason is that once you count for cell division as well, you get such a mess of algebra that I think you're missing the points that you're trying to study. So my feeling is that if you're studying the effect of cell division and segregation, include it. If you don't, then we always ignore it. We only just put it in, many papers we put in the supplement saying, we repeat all the calculations when we have cell division as well. I can't remember if we did it for this particular case, but certainly every other paper we did, it turns out more or less the same. It's not such a different thing. This might relate to Andrew's talk yesterday. I think where he emphasized the importance of cell division. It's not cell division that causes the system to bounce back to an average or create finite relation times. It's the difference in kinetic order between the production and degradation. So if you have constant production and exponential decay, if you go above average, you're moving down. If you go above average, you move up. Cell division is also more or less a first order process, just that all the events happen at one point in the cell cycle. So in fact, Andrew did the same talk usually does. The example where you have Poisson production and binomial segregation, that just gives you a sort of walking Poisson distribution throughout the cell cycle. And at some point in the cell cycle, that's exactly the same distribution as you get with this. So it's not the perfect approximation, but we use this almost always to approximate cell division. And that's so that the math becomes more tractable and we can see other things. And once we put cell division in there, it just gets messy. So my guess is that it is also true for cell division. I would be extremely surprised if cell division would change something in time. All right, so that's a 15-minute introductory slide or something. All right. The other thing we're trying to work on is to see, can we also expand in topology? Because that thing is the big killer, is that it's not that we don't know the parameters of the rate functions. There was, Joe mentioned a quote the other day that if you model fits all the data, it must be wrong because not all the data is right. I think that's a very conservative view. I guess most people move from theory to experiments. They start out doing these naive simple models, and then they start adding more and more realistic things. Our path has been the complete opposite. the more experiments we do, the more we realize that it's not that a few parameters are missing. It's that you don't know the topology of the network, you don't know the rate functions, you don't know if there are spatial effects or no spatial effects, you don't know where the noise is coming from. Many methods, there are entire fields where the results are just pure artifacts of the methods. That's something we worked on quite a bit in the beginning. We set up the lab just trying to fix the experimental methods. So I think that if you still want to do something, it might be that's meaningful mathematically and in some way rigorous, but you don't want to get into this garbage in, garbage out situation, then you have to find some way of making conclusions that are independent of most of your assumptions. And our way of doing that is to say, what if we specify a part of the system, but it's embedded in a complex cell, and you allow feedback loops, and you allow any dangerous thing to happen here. You allow spatial behavior. This can be sort of, you can have millions of variables and still have a non-macro process. And we just say, what is rendered impossible for these two variables by the parameters here, regardless of how you embed it. So it's a way essentially of doing modules that people have looked at, like in coherent feed-forwarders or something, but instead of looking at the module on its own and saying what it actually does, we're saying what cannot the module do? It's a function of the parameters, regardless of how it's embedded. And so now essentially we can take, it's like you have infinite master equation approach here, but you have marginal master equations for the specified components. And you can, if you want, you can essentially dedicate a billion variables just to say that one molecule makes a dance around another molecule. You can do anything you like, essentially. And there we see, is there anything you can derive about this system? So we try to then predict some statistical properties, the function of some parameter of the specified part, and see are there any inaccessible regions, something that is rendered impossible. This is something we pushed for 20 years. This is something where the papers take at least 5, often 10 years for us to finish. So far, every time we take a different constraint, like lags, delays, finite signaling rates, so forth, we end up in a different area of mathematics. And I'd say the main take-home message we've gotten from this is that negative feedback has an incredibly hard time suppressing fluctuations as soon as you count for any realistic constraints. And for the control theorists, that might sound like that can't be right because we studied this for 100 years. It turns out that many of the central resolvable control theories say, for example, that sharp delays are bad, but if you have a lag that's exponentially distributed, then it's not so bad anymore. It turns out that once you account for the discreteness of the state, then, for example, lags are as bad as delays almost. And the limits that you impose on the system can be quite different. Right. So recently, we've been working on this not for concentrations, but for timing. That's supposed to be the real talk, so that was just the introduction. You see, in the chemical reaction network, to what extent can you get oscillations without too much phase drift? Can you get timing between the start and the end point? And the analogy here essentially is you have a grandfather clock. You engineer it such that every single swing of the pendulum takes a fixed amount of time. And then every time you swing, you turn this cog, and then you can count the number of steps. Chemical systems, that's hard because the individual transitions tend to be exponentially distributed. And counting the steps is hard because who's going to count the steps except for a chemical reaction network that itself fluctuates? So how can you do that? Well, there's a beautiful proof in probability by David and Larry 20 years ago, where they looked at bounds on first passage times in arbitrary time continuous marker process. Essentially, we have a network. This is just for n equals 3. Let's say you want to go from 0 to 3, and you want to make sure that the standard deviation divided by the average is as low as possible. How should you design all these rates? What they showed is that the way to do it is to always have an irreversible unbranched chain from n to 0 with the same constant rate everywhere. First time you see this, you might say it's trivial because constant rates means that there's no rate limiting steps. And then you might say, well, what if you had something like this? It went from 0 to 1, 0 to 1, 2, 0, 1, 2, 0, 1, 2. You can make a million loops here, and then you can average out all the noise. Why does that not improve things? Simple intuition is that if you want to cycle around, you have to have a way to break the cycle. And that means there must be a choice here from 2 to 3 or 0. That means you come to position 2 and you flip a coin. Should I go this way or that way? That means you get a geometrically distributed number of cycles. That means the standard deviation in geometric distribution is as bad as a single exponential step. By introducing a cycle, you can't beat what a single step can do. So that's a beautiful proof. There's been these 10 papers in PRL and single molecule enzyme kinetics building on this. So the field is called sometimes statistical kinetics. There's a bunch of new results in cell biology. They all essentially say the same thing. You should not have positive feedback. You should not have negative feedback. For timing, you should just have unbranched reversible chain, constant rates. But the one thing that has not been considered here is that in most chemical systems, you just can't, even if you have an unbranched chain, you can't ensure that the number of steps is constant. If this is some molecule that decays to zero, the thresholds aren't perfect. And your starting points won't be perfect. You might make like a burst of gene expression, and then you have to decay that down. You don't always start with exactly 100 molecules. Sometimes it might be 90 or 100 or even 200. So we ask the question instead of saying, if you have unavoidable variation in n, to what extent do you still get the square root of n rules? To what extent is it still true that this topology is optimal, and what should the rates be? And that's something you can do in many different ways. So one thing we did here is to say, let's look at an arbitrary network, but let's say we fix the end position to 0, but we pick a random starting position, and we ask the first passage time to get to 0. And then it turned out you can expand their proof, and it's still optimal to have an irreversible unbranched chain. But with a restriction, that chain has to be organized according to the probability of the starting position. So the most likely state should be most removed from the end. That's very difficult to achieve for most systems. If you make a number of molecules, you'll have some distributed number of states, but typically for degradation, you go from 109 to 98. You don't go from 100 to 77 to 121 to... You can't arrange necessarily states according to probability. The other thing is that you can no longer have constant rates. So this is something we looked at quite a lot for different types of scenarios like this. It turns out that if you have equal probability of starting any position, then the bound is in fact given by the inverse fourth root of n. So it's can be very, very restricted. Then you can ask systems, okay, what happens if we cannot rearrange the probability? What happens then? Then it turns out that for many of these systems, it's no longer even optimal to have an unbranched reversible chain. You can prove that it's always optimal never to branch out. You should never have a choice between two paths. But you can have sort of coalescing things. You can have branching in. You have different starting points and they need something. And then you can come up with conditions for the starting point distributions of when those branches aren't optimal either. So I'd say that the natural science message here, I guess, is that the topology of an unbranched chain turns out to still hold, but for much, much more involved reasons. Because now, before it made sense because the unbranched irreversible chain was the longest, that maximized the number of steps that you can get without introducing randomness in the number of steps. And then you can have constant rates, and that minimizes the threat of rate limiting steps. Now suddenly, you'll have enormous variation in the number of steps. You will not have all steps be equal to rate limiting, and it's still optimal to have this in almost all situations. And the main issue here is the rates. You can only take advantage of these kinds of chains if you can optimize your rates. They should no longer be constant. Why is that? Let's look at the case before. Let's say we have deterministic degradation with zero-order kinetics, like in saturated enzyme. You start with n, you go down linearly to 0. You start with 2n, it will take you twice as long. So constant rates will just propagate all the noise in n to noise in the timing.
Johan, can you give me an example? What sort of problem are you thinking about? What sort of biological problem are you thinking about?
So I'm going to have two experimental systems in the end here. Essentially, it's things like how do you create an oscillator that actually keeps phase, that actually keeps the time, like circadian rhythm. It doesn't need all the input from the sun, but actually just intrinsically keeps on doing it, as opposed to just random reactions going on the phase. Or self-made decisions, or...
So it could be a relaxation oscillator or something like that.
Yeah.
There was a question in the pause. Are you allowing yourself to have quadratic decay also?
So we are considering the arbitrary rates, so you can have
I see.
any
Okay,
normal
so you
Conti
can
function.
throw that in.
Yep. I'm just giving two examples here for intuition. So here see that zero decay is terrible when variation in n. First order decay is much better because if you start twice as high, you're only adding one half-life. If the entire process down to the threshold takes 10 half-lives, that's just a 10% change in the time for a twofold change in the starting value. So first order decay is much, much better. But of course, as people have noticed before, if you don't have variation in n, and you just look at the random path, then zero decay is the best thing because you have no rate limiting steps. You're maximizing the equal steps here. Exponential decay is terrible because if you start with 100 molecules, the last step from 1 to 0 is 100 times slower than the first step. So everything is dominated by what happens down here. You think you have tons of molecules, you have thousands of molecules, doesn't really matter. If you have millions of molecules, it actually doesn't matter because the series doesn't converge. But the last few steps dominate everything. Very simple solution. What if you just take the sum of these two? You have both reactions in the system, you take the sum of these. What happens then is that in the beginning you have way too much. Very quickly you suppress that. And then once you come to low values, you don't get this 2 or 3 rate limiting steps, but you just slowly put up that. It turns out that for many star distributions, you can calculate, again, this sort of Bellman approach for optimization. You can calculate the exact rate function. It turns out it's always monotonic, so the optimal thing is always monotonic, and it's always increasing. This is an example. And it turns out that for many distributions, this very simple thing, even though it looks very different from the shape of the optimal curve, it turns out the performance is not that different from the optimal performance in terms of the standardization. Right, so now to Joe's question about what kind of biology are we looking at here. So the first thing we looked at many years ago was this timing and self-made decision in bacteria. Essentially, Bacillus subtilis goes in a free-living state, and then it decides to form a biofilm, and it starts chaining. And this decision is reversible, so you can form a chain, and then chain just means that you stop dividing properly. It's not that you aggregate, you just, at division, it becomes like a sausage string, like you just keep on adding length. So we built a system where we could have reporters for those cell states and show that the red reporter does correlate perfectly with the chain state and green with the Motown state. We built these microfluidic devices, sometimes called mud machines. And we added these feeding trenches on the sides and uniform feeding everywhere. And we can make sure that over hundreds of generations, sometimes run this for 1,000 generations, you have perfect uniformity in the growth of every property here versus here, or this trench versus this trench. And then we get these chromographs. So here's an example of one of these trenches over time. So this means that the cell is motile, suddenly forms a chain, it's kind of chaining and jumps out again. And now we can get essentially time intervals for how long it's staying in state. Here's an example of a curve that comes out of this. It turns out that on average, they stay about 85 generations in one state, and then on the order of 10 generations in the other state. And the motile state, you have almost a perfect exponential. But in the chain state, it turns out there's a strong memory. This is something you would need essentially 9 equal rate limiting steps in a perfect chain in order to get 30% CV. So you might think 30% doesn't sound so precise. For timing, it's not bad, given the exponential nature of the events here. You can also genetically show which part of the network affected one or the other, and everything was very modular. So you could completely mutilate part of the network, and some properties were quantitatively intact, and other properties didn't change enormously. So just we're about to publish this, we realized that we were scooped for the principle. Turns out that the Ig Nobel Prize was given to a paper that showed that exactly the same thing. Cows are motile for an exponentially distributed amount of time, but as soon as they become immotile, they have a very nice cyclic distribution. It's almost exactly the same phenotype for the cows. So in most of our papers, I try to sneak in some sort of joke. I've been told this is very unprofessional, but we do it anyways. So I asked the editors, is it okay if you make a straight-based comparison to the cows? And you can maybe alert the news and news writer, which they did, and but they didn't alert them to the fact that it was a joke. So, there's a whole literature of this, like news picked it up on it, Nature Physics picked up on it, Scientific American picked up on it, and it's all about the mysterious connection between the cows and the bacteria, how they have the same behavior. What we can do that the cow people can't really do is try to see, can we explain this in terms of chemical kinetics? We're not going to try that for cows. Even with bacteria, it's not so easy. The two main features here is that you have a very stable, distinct behavior for hundreds or many tens of generations in one state, and about 10 generations in the other state. Then you typically suspect positive feedback. You go into state and you lock into that state. And then you have this timing precision, and very naively you might say, timing precision, you should have negative feedback. Turns out it's actually the opposite. Many times you have positive feedback with timing precision. This network had tons of positive and negative feedbacks that were reported in the literature. But we also realized that it had one of our sort of favorite schemes here, which we heard talk about the other day about molecular sequestration, where essentially two of the key controllers form a complex. That complex, as people studied to death, you can't find a single thing it does in the cell. This doesn't seem to do anything in the cell, but this guy here represses the target genes. And then we realized this is very similar to a scheme we had studied for many years. And it turns out that if you just look at a simple model where you say you have Poisson production of a burst of one, Poisson production of a burst of the other, constant rates, uncontrolled, and then some exponential decay, assume the same rate constant here, because in reality it's dilution and division. And then you have complex formation. So we know the parameters in the system. The complex formation is incredibly strong. So essentially they can't coexist. As soon as both are there, all the pairs will form, and it's almost irreversible. So irreversible at time scale where dilution and the cells get rid of it by growing and dividing. Which means that in the time windows where x1 dominates, you can replace this by a one-dimensional scheme where you make x1 it's a burst, it decays exponentially, and then you remove x1 every time that there's an x2 production, and then you remove b2 of it. This obviously you can't put negative numbers, obviously, so this is an approximation. Now, if you look at this scheme is not so different from the scheme I told you earlier was close to optimal for timing. Right? We have maybe variation in the production burst, but your elimination has a first order term and a zero term. And that means that even if B1 here is extremely variable, your exponential decay is going to cut that variability enormously. And once you come down to low numbers, this term is going to dominate. And if B2 is small, which we think it's one in the system, we think B1 is very high, B2 is very small, then you just boom, 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 boom. So an open loop system, no feedback, no control, just randomly produce bursts, and you have this complex formation. These are, I think, the two types of mechanisms in biology that have become most notorious for making noise. Random bursting and sequestration. So sequestration is very similar to dynamic instability, microtubules, and so forth. It's essentially a close to unstable process. So we just looked at it briefly, and it turns out that you can actually get these quite long-lived windows, and they replace each other back and forth. So in the lab, we call this the Scrabble system. So I started studying this after I used to play Scrabble a lot, and I felt like in the beginning you have a few vowels and 2 consonants, and then after an hour playing, I'm always stuck with something like this. Like one vowel and all these consonants. And I used to say that the universe somehow conspires against me because this can happen 100 times in a row. And then I came up with this sort of self-glorifying explanation, which is that because words are sort of stoichiometric, they consist of both, the temporary half-life of the minority component is shorter than the other ones. So if you have one vowel, you'll use it, and then you're back to the other ones. Unless you trade in your letters, which is the equivalent of decaying things, you can't avoid the fluctuations. Unless you memorize that this is actually a word in the Scrabble dictionary. It's a Welsh instrument. Which cells could maybe do as well, that when they have a surplus or something, they build something else. If they don't do that, you can again use these sort of generalized proofs and say that it doesn't matter how the two components control each other, there are hard limits on the fluctuations you have in these molecular sequestration systems. As a function of the efficiency, a function of how many molecules form complex versus test degree. How much do you make words versus just trade in the letters. So I went back to the system more carefully and said, can we actually explain all these quantitative features with a very simple model with the same dilution term? C you can set to infinity to reduce the parameter. So essentially we have only 2 parameters, not 2 free parameters, but 2 parameters in the entire model. And those uniquely determine the average abundances. So we know essentially everything about the system. Turns out that every single feature we observe, the 2 distinct states are very, very long-lived. The exponential interpeak time and the narrow peak times, they all come automatically from the theory. You don't have to tune parameters or anything. There's only 2 parameters in here, and everything is explained by that. So then we ask, what about all this other crap that goes on? We know that there's positive feedback loops. We genetically knock them out. Nothing happens. All these loops that were reported, they don't seem to do anything to this circuit. Then we went in and changed the parameters that matter, because in molecular sequestration, if you have a narrow balance, if you make more of one than the other systematically, you can change the balance completely. That's exactly what happens. And some control circuits are seen to be there just to make sure that the rates are similar to each other. Then we said, okay, because we're always nervous about this issue of uniqueness in biology, that there are so many explanations to fit the same data. So we tried to see, okay, the math fits everything perfectly, and it's biochemically motivated. We perturb key parameters, everything works as expected. We delete all the parts that we don't think matters, everything works as expected. But if this is really true, then it's only the two open reading frame, the amino acid sequence of the proteins. That's the only thing that matters here. We should be able to take in a different organism, synthetic promoters, constantly on, no control, and we should get the same behavior. So we move them from Bacillus subtilis to E. coli. It's 1 billion years diverged evolutionarily. Doesn't have any of these pathways. You study hundreds of promoters in E. coli, and as soon as you put in these two open reading frames and the synthetic constant promoters, E. coli start doing exactly the same thing as Bacillus subtilis. This is the paper I mentioned the other day that was in review for 3 years or something. It just came out a week ago. Right, so we're quite happy with this for 2 reasons. One is that self-made decisions, the explanations tend to be very complicated, tons of feedback loops. I only have 2 more minutes.
Carry on.
Tons of feedback loops, very complicated. This science paper saying there are 7 interconnected positive feedback loops that are somehow creating these things. Here it's something absolutely trivial. And not only is it trivial, but it's interesting from a stochastic point of view because the deterministic equations here only have a single globally stable steady state. Nothing interesting happens deterministically here. It's all in the noise of the sequestration. Sequestration is everywhere in biology. And if you want different distributions of times, that's easy because, for example, if you have an exponentially distributed lifetime of an mRNA, then you often make a geometric distribution number of proteins. So the shape of the RNA decay curve that essentially tells you the time window for making proteins. So it tells you essentially the shape of the distribution for the peak of proteins. If that decays linearly, that then converts to the time that you're in that state. So you can say that this mRNA lives for 1 minute, but the shape of that lifetime becomes the shape of the self-made lifetime, even if that can be on a time scale that is 1,000 times longer. So you can have these microscopic events and just mirror them on the macroscopic scale. So all these small details that people ignore in the sort of wiring diagrams, they can be exploited to get this very precise behavior in almost any behavior you like. So we kind of think that the explanation to these things, maybe for mammalian systems as well, is kind of hidden in plain sight, that it's the sequestration that's doing it. Right. So very quickly here, for a synthetic example for the repressor later, maybe most of you have seen this already. Repressor X suppresses Y, repressor C represses X. Beautiful example. They were very honest about the fact that it didn't oscillate in most cells. Only 4% of cells showed any sign of oscillation. And this was the best one, I think. Most of the other ones are quite noisy. And there's all these reviews saying biology, real biology is more complicated. There's redundancy and all these things. And we thought that this actually was a very nice way of doing it because the more stuff you put in, the more you have like a whispering game. You lose information in the Shannon sense. And once you lose information in Shannon sense, nothing you can do. You're doomed to be imprecise. We thought this should be a great system. Why doesn't it work? So first thing we did is to see, could there be some weird interference from the plasmids? So we put 2 reporter plasmids, live pin M cherry. We waited until the M cherry was lost from the cell spontaneously. So in very few cells, it disappeared. When that happened, the repressor later became much, much better. So it's nothing to do with the circuit, it was just this thing here. Turns out after another 10 constructs and analyses here, turns out there's 1 amino acid on the reporter protein that interferes with the proteases, that interferes with the repressor later. So that's not something that you could ever have expected. So all these papers that said we can now capture all the noise of the repressor later with a model, this is why I don't believe in the simple models, is that 1 amino acid on the reporter and it just completely can change everything. So then we said, okay, let's now, it's still not perfect, it oscillates, but it drifts out of phase very quickly. And all these synthetic oscillators, they oscillate. Many of them oscillate in like a few % of the cells, and many of them don't actually oscillate at all. They have the same frequency of oscillations as you would get flipping a coin. You get head, tail, head, tail, head, tail in some percentage of the cases. But there are real oscillators, but they all drift out of phase very quickly. So we said, let's go back to the theory and see if we can improve it further. What we did here is something that sounds a bit absurd maybe. If you haven't heard this theory, which is you're supposed to have an odd number of regulated repressors. What we have is here now a 4th repressor. It's produced at a constant rate, just randomly rejecting more repressors in the system. And that goes in and interferes and binds to one of these existing repressors. So it sounds maybe weird from that perspective, but what we've done here is that we've taken away this exponential decay, because some of these repressors go down almost down to the 0 before they de-repress the next one. So you can have thousands of molecules, but the transition happens in a regime we have very few molecules. by doing this, we make sure that, yes, you have an exponential process initially, but eventually you start boom, 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 instead of having the last few steps to be dominant. And we do this in many different ways. We do DNA binding sites, protein substitution partners, and long story short, we can get incredibly precise oscillations. You can, we haven't published all of them yet, but some of them oscillate for 500 generations before drifting out of phase with even half a period. And the period is exactly the same under all conditions we're trying, even in the material that comes from the gut of a mouse. So now we can feed mice. This is with Pam Silver's lab and David Brigler. We feed the criteria expressed in the repressor, feed them into mice, give them some IPDG in the water, so now you synchronize the oscillator, and then you can see by how much, collect the poop, and then see how much did the oscillation shift. It tells you how many times it divided in the host. You get exactly the same result if we just kick out the matter from the gut and do it on a microchip. This is our next hope for a global price, I guess. All right, so this is almost my last slide. So that's something that we did quite a lot. And with all these tools, we spent many years to make sure that we get very precise microscopy. We developed tools to make sure you can count every single molecule in the cell. But then we had some problems where we looked at very rare events. We needed many, many more divisions. So every year we try to push the throughput. And we roughly increase the throughput a factor of 10 about every 18 months. And we've been doing this for many years now. So right now we have about 1 million trenches that we can track in parallel. And that means imaging every 5 minutes. So we get quite high frequency images. So this is all about pushing whatever's rate limiting in the stage of the microscope, illumination, just trying to push the engineering. We can do it for 30 different bacteria. We've done it for yeast cells. We do it for mammalian cells. We also developed something that's just coming out in the weak in nature methods where we can retrieve any cell of interest. So we can now look at 1 million mutants. Look over long periods of time so we can sample the process. We look at long-term dynamics, spatial processes. We don't have like the cell sorter issue that the cell flies by and whatever state you see it's in is all phenotypic noise. Here we are building up histograms over time so we get all the information about the strain. We can look at thousands of tens of thousands of cells and divisions here per strain. And then based on that information, we pull it out and sequence it. And that turned out to work really well. This movie somehow didn't play when I showed it earlier. It's supposed to show you how you pull out a cell around. This one works. Just take an IR laser, grab a cell, and then it's going to play here. We put it over to the other side, we release it, we capture it, put it on a plate. So we just showed us a proof of principle here. We spike a large amount of dark cells with a few yellow, a few red, a few green. Then we try to pull out 3 red, 3 yellow, 3 blue, 3 red, 3 yellow, 3 blue. You've never seen a mistake. You never see any harm to the cells, and there's not a single mutation caused genome-wide by the approach. So we can essentially see in an evolved system, we can see any mutation. What is good. So now I'm looking at what if we try to build the same kind of circuits as before, but without thinking so much, without trying to optimize all the rates. So we say, let's come up with a topology that we like, this repressor with titration, for example. And then we look at, we built about 500,000 mutant oscillators. And then we spent half a day or a day screening them. We pull out the winners. We do the same thing for the hasty oscillator. Build 500,000 mutants, screen them per day. And immediately in the first screen, we get almost perfect oscillators on almost any time scale. So we can have oscillators that keep phase beautifully with a 50-minute average period or a 20 generation average period. Just by changing some of these promoter sites and reversible binding sites. So, I'll just skip this. So that was it. Essentially, we're now taking these methods, we're pushing a lot of these microfluidic methods for different organisms. We're trying to make things where we can do the single-cell RNA-seq, for example, in a time series. So we look at a cell, as soon as it divides, we take one daughter and we do single-cell RNA-seq. We are developing tools to look at full ecosystems on chip, to look at genome-wide libraries by developing the various labeling techniques and so forth. So that has really changed the lab, I think, that now suddenly our experiments are much more reliable, we get much more throughput, there's much more data. So the turnaround time that used to be many months when we started is now more like a few days. So that's one reason we also start studying a lot of different systems. So the people here, Nate and Tom, did a lot of the work on the, together with Rich Losik, on this self-fake decision. And Laurent did almost all the work on the oscillator. and all the others here are also contributing to the basic setup.
All right, thank you. So I think in the interest of time, we'll delay questions to after coffee. Did you want to maybe extend the conference break?
Why don't we come back at 10 to 11?
10, 10 till 11. Okay, great. Okay.